So we're going to have this equation for liquids and solids, which is the change in entropy equals the CV average and the natural logarithm of the temperature 2 over the temperature 1, and this C average is the average of the specific heat of the substance of this given interval of temperature. And in the case of liquids that expand considerably with a change in temperature, we're going to have this equation, and this states that temperature 2 equals temperature 1. And this is an isentropic process because there's no change in entropy. And now, for ideal gases, we have a different equation, and we are going to have two different categories. One is the constant specific heats, and with variable specific heats, we are going to have another equation. So for constant specific heats, this equals the integral of the two reference states of the Cp in the given temperature, the change in temperature over the temperature, minus the constant R of the in natural logarithm of the pressure 2 over the pressure 1. So this Cp is the one that we can find in the property tables at the given temperature. And for variable specific heats, we're going to have that the change in entropy equals the reference state. It's the temperature to be determined minus the reference state of the integral of the Cp, and the Cp is also the one that we can find in the property tables. And so now this is for the change in entropy, and we're also going to have a reversible steady flow in these processes. So the work done is going to be equal the negative of the interval of the two states of the volume times the difference in pressure, minus the change in the kinetic energy minus the change in the potential energy. And there's a process that is called that it's the Bernoulli equation. So it's whenever a steady flow of a liquid through a device that involves no work interactions. This type of systems is going to be applicable to the systems that we saw before. So for example, nozzles and pipe section, and the work is always going to be 0, and it's the volume times the difference in pressures plus the difference in kinetic energies and plus the difference in potential energies. The C is going to be the height, the difference in heights. And as I said it before, we're going to have inefficiencies and in these processes because we have inequalities and irreversibilities. So we're going to calculate the efficiencies of the steady flow devices. And the case of isentropic, as we saw in chapter 6, we're going to have a model that we can use to determine these efficiencies. In the chapter 6, we had the Carnot principle and the Carnot cycle, and in this, the model process is going to be adiabatic, since adiabatic means that there's no heat transfer and with no irreversibilities. So this process, as I said it before, is going to be called the isentropic process. So the isentropic process is going to be our model. And when we have turbines, the way we're going to calculate the inefficiencies or deficiencies is going to be equal to the actual turbine work over the isentropic turbine work. So because we're going to calculate this difference in work, and we are going to substitute with the enthalpies, so it's going to be equal to this formula. And whenever we have pumps and compressors, it's going to be the other way. So it's going to be the isentropic compressor work over the actual compressor work. So that's why we're going to have the H2 minus the H1. And for the nozzles, as whenever we have a nozzle, we're going to focus on the kinetic energy. So that's why we're going to have the velocities. And we're going to also have this formula, that it's the enthalpy 1 equals the enthalpy 2 plus the kinetic energy. And finally, the entropy balance is going to be calculated as the energy balance of any system we have, but taking into account that there's a generation of entropy. So the change in the total entropy of the system is going to be equal the entropy entering the system minus entropy leaving the system, but we have to add the entropy generated. So we are going to have this formula, and that's it.